tutorial, we are continuing with blockchain applications. We are continuing with the case studies. So in this tutorial, I'm going to cover the case studies of document-based records and of PowerLedger. So document-based records on blockchain. The idea is usually you do not store the documents themselves on blockchain. You store them in an external storage, such as a specialized database, and then you secure the storage in the chain. For example, you compute the hash of the data stored in the database, and you put that hash on the blockchain. That's a common idea in a hybrid storage. And in particular, it's common. So what is the solution for the offline part of the storage? One frequently used technology in this context is the IPFS. So IPFS provides file sharing peer-to-peer network, and it stores and shares the data in distributed hash table. I'm going to cover IPFS in my very last lecture in this course, so the last day. So I'm not going to expand much of it now. But so why do we want to store document-based records on blockchain? Well, it's the usual fare. It's paperless, right? So it helps with the digitalization of the society. It provides better transparency for the purpose of auditing. It enhances verification, and also sort of long-term, hopefully it develops higher trust in the society, for the society to higher trust in the infrastructures. And it's also cost-effective. So let's talk about challenges, but also applications. So what kind of documents? Well, in the first lecture today, we have already seen how government of India is storing land property information on chain. So that's one example. So grade certificates and diplomas is another common example. And some universities in Europe basically put all of their diplomas on the blockchain. Okay, what next? Insurance records, immunization records, which was like very important during the COVID pandemics. Health-related record, know your customer information, government-issued certificates such as driving license, and so on. Those can also be integrated with digital identity management, and can be stored in personal data wallets. The challenges, of course, are multifold. So one of the challenges is obviously consent management. So management, or generally speaking, management of access to the sensitive documents, and data privacy upon the management. So strict access control, but it's much beyond the access control. So tomorrow, when describing the application or the use of blockchain in healthcare, I'll talk about consent management in that context. So there is a need to integrate with a variety of cryptographic solutions in order to address these challenges. Now we start with a case study of certificate chain, or cert chain in brief. It's yet another project developed by the Blockchain Center under the government of India. So in cert chain, You have internal blockchain storage, and then it would be used, or the idea is to use it by the police department, professional courses, government department, but also accreditors, validators, testers, and a number of local bodies who would be storing, for example, birth certificates, and also educational institutions. So again, like the number or the variety of certificate that can be stored on the system is very high. So the architecture of short chain is very similar to the architecture of other similar systems. So it's very similar to the architecture we saw in the first lecture today. Again, you have the short chain and the portable database as the core. Again, together providing hybrid knowledge. You have services built atop the storage solution, and you have API towards individual types of users. So that part is again very similar. You've already heard 2 lectures today on smart grids. So I guess this is just a very brief summary. It's a subset of what you have already seen. But the point here is that some of the smart grid is standardized. For example, NIST is the standardization body in the United States. And in particular, it has standardized the framework for smart grids so as to allow individual organizations or operators within the framework to be hooked into the framework, to connect to the framework. And yeah, so this is NIST framework and roadmap for smart grid interoperability standards, release number 3. Interoperability standard means, again, like how different entities or entities of different types could adhere to communication standards when building a holistic infrastructure. So as you can see the amount of diversity exhibited in the framework. So there is there are service providers, operations, distributions, markets, smart homes, smart hospitals, smart installations, and well, variety of smart meters. And in the commercial world, there is like how we build automation in this infrastructure. So yeah, it's just continuation of the standardization effort, conceptual reference model, where you can see the functionalities of the service providers, operators, but also markets and bulk generation, with the customer connected to the infrastructure for internet and e-business solutions. All right, so now we are coming to the interesting new part, namely how blockchain can be used to support smart grid. Again, you've already seen some of that, but I'm going to expand on the variety of different functionalities and benefits that blockchain can bring to smart grid. So you have peer-to-peer energy trading, where the energy trade would be more like bottom-up, would not go through some centralized organization. So that's the meaning of peer-to-peer, direct trade between producers and consumers. And in this case, smart contracts may implement the paper-based contracts and regulate the trade. Grid management. So there would be, the grid needs to be managed, like all different elements in the grid, and so the grid can also be federated, namely it may consist of microgrids, right? So how is the architecture recorded and how is the information flowing between different components in the grid represented in storage? So grid management and the configuration of the grid, all this information can be stored on-chain. Green certification and e-mobility is something I'm going to cover in next slides. Energy theft detection as well. But smart grid, a combination of smart grid with blockchain can increase consumers' trust in energy billing and reporting and in the verification process. So this is one particular proposal to use blockchain in the context of smart grid management. So here you see that there is a variety of microgrids connected to the power grid. So microgrid means regional grid or a grid within, say, a neighborhood. So there could be like it's called a smart neighborhood in the context of smart grid, and those smart neighborhoods, they may be self-arranging in the sense that there is no single central body which overviews the emergence of different smart grids or microgrids. So how do they self-organize? That's one question. How do they ensure secure transactions and communications between them? And how do they report the information about the operation? So there is a cloud-based monitoring and reporting and storage, of course. And there is a hybrid architecture in the cloud. And that hybrid architecture takes advantage of the chain. So this is a proposal due to the Smart Grid Energy Management on Blockchain project managed by Dr. Moody. Another use case would be blockchain for e-mobility. So in blockchain for e-mobility, there is, so this is about the infrastructure of charging, for example, electric vehicles. This is just one potential use of the framework. So in this framework, different electric vehicles may be moving along the road and maybe, of course, maybe connecting to the charging stations. But sometimes, instead of connecting to the infrastructure, such as the charging station, they may connect to each other, and so it may be possible to conduct a trade between two electric vehicles. For example, one electric vehicle has significant amount of charge left in the battery, while the other vehicle urgently needs to charge the battery. So in this case, instead of using the infrastructure, it's possible to connect the two vehicles. However, the main challenge, of course, is how to discover potential buyers and sellers at a given moment in time in a given location, but also how to conduct the transactions in a safe and secure way, how to perform the payment between the two participants. So all those questions all those questions need to be addressed by the framework, and again the framework supports all such transactions and communication. Yet another example would be tracking emissions. So in this case, usually in the industrial world, there is a quota of allowed emissions. So a factory or a ship or a given industry is allowed to produce only a certain amount of emissions. And of course, there are those initiatives about green computing and making the world greener in general. So those initiatives try to bring the amount of initiative as close to zero as possible. Well, of course, it may not be possible to eliminate emissions completely. So anyway, there is a certain amount of quota. Now, if, say, the industry goes over the quota, the industry would be fined for that. If the industry manages to do better than the quota, there might be some benefits for the industry. For example, the industry may be given credits, and those credits have also financial value, so they may be used in the future. They may be sold as a token to other industries. So therefore, there is a need to provide the framework for emission trading and credits. So in a paper, a permission blockchain-enabled trustworthy and incentivized emission trading system, they came up with a conceptual framework for such a trade. And the framework is based on blockchain and based on a variety of contracts. There is a bidding contract, a trading contract, and a selling contract. Selling, obviously, from the seller, bidding from the buyer, and the trading contract when a match is found, they sign a trading contract, which regulates the relation between the buyer and the seller, and all those contracts are executed and registered on distributed ledger. Yet another application. Yet another application I would like to mention, or another use case, is energy theft detection. So in this illustration, again, something you've already seen from the lecture on smart grid, there is a utility provider in the center, and then you have different DSOs or DNOs in the architecture. So each DSO would be responsible for a subset of consumers. So you can see it as another type of federation. And we also need to differentiate between electricity flow and data flows in such an architecture. So that's the architecture. Now, what's the problem? The problem is that sometimes the energy consumption may be underreported. Why would it be underreported? It could be underreported because of a faulty smart meter. It could be underreported because of deliberate tampering. So how do we distinguish between the two, and how do we detect that something fishy is going on? So in the paper, Designing a Blockchain-Enabled Privacy-Preserving Energy Theft Detection System for a Smart Grid Neighborhood Area Network, so the authors proposed such a conceptual framework. And the framework is again based on blockchain, but using also sort of not specially crafted, but specially carefully selected cryptographic primitives. So the idea of the framework is that So there is again a contract for energy consumption, and the data is being sent to the cloud in real time, and it's also analyzed in real time. And it turns out that the performance can be sufficiently good in this kind of scheme so as to allow real-time detection. So these are some performance numbers to support that the framework is able to detect energy thefts or leak of energy, and also classify the cause of the leak. Also, in the upper tables, what you can see is the comparison of the actual energy consumption and the reported energy consumption. So this information is just for our benefit in order to be able to assess the success of the framework. This information is not directly available to the framework. So we can see that under-reporting is going on, but in some cases there is even over-reporting. So this is like the ground truth. This is what's going on, but that information is not available to the framework. Instead, the framework has to monitor it by itself, and what you see in this table is the result of the monitoring and the detection outcome. So the framework classifies the outcome according to different types. So it could be energy theft, it could be faulty smart meter, and over-reporting is obviously faulty smart meter. Now the last table in this slide shows the performance of the system. So it shows the latency, the total latency. The total latency includes both the latency of the communication and also the latency due to the analysis. So it's combined latency. And as you can see, the the system is able to provide a high amount of transactions per second, and cope with it, and also at the same time provide low latency for the detection. So why to go for this design alternative? Why use blockchain along with carefully selected cryptographic primitives? So of course we could deploy more smart meters. If we deploy multiple smart meters, it becomes more difficult. It becomes less likely that all smart meters will be faulty. So we will be able to overcome the failure of a smart meter. However, this requires extra cost for the devices. So that's the downside. Next, we could also use machine learning approaches in order to try to detect and classify the faulty behavior. So what's the problem? The problem is that usually it requires significant amount of processing and training. And in particular, in order to train the model, you need sufficient number of historic data. And if what happens today, so today there is a heat wave, but the last month there was no heat wave. In this case, the data from the last month may actually be misleading for the model. So the accuracy may not necessarily be very good if using machine learning. And additionally, we need significant amount of data, and also the interpretation of the result, the detection based on the trained model would also take some time. So it's still a valid approach, but not without drawbacks. While the blockchain-based architecture does not have those drawbacks. Okay, next I would like to talk about the case study, a different case study of the PowerLedger. So PowerLedger is, as of today, probably the most popular blockchain-based platform for power trading. So it actually provides a variety of functionalities: peer-to-peer trading, a microgrid and embedded network operation and management, carbon trading, transmission exchange, distributed market management, and quite a few other functionalities. So it's a blockchain project for energy applications at global level. One of the recent news is PowerLedger powered with Solana. Solana is yet another cryptocurrency which we have not covered in this course. But it's based on the proof of elapsed time, similarly to Sawtooth, and it's one of the cryptocurrencies providing perhaps the highest throughput of transactions. So, so PowerLedger has actually two tokens. So it's like two cryptocurrencies in one. So one token is a higher level token, power token, but there is another token called SparkZ, and that's like a lower level token. So this the main token exposed to the external applications power token. So one could say it's the main token from PowerLedger when interacting with external applications. And thanks to this token, the PowerLedger provides decentralized solutions for producers and utilities to track, trace, and trade energy efficiently within local markets. So here is an example of how peer-to-peer trading is done in PowerLedger. So POWR tokens can be used directly in peer-to-peer trading between producers and consumers. Consumers and producers are collectively called prosumers. So it should be between producers and consumers with near zero intermediation because it's a peer-to-peer trade. And as mentioned, dual token ecosystem, where SparkZ tokens are priced, issued, and redeemed in the local currency, and POWR tokens allow access to the PowerLedger applications. So you see some examples on the right-hand side for retail applications and for peer-to-peer direct transactions. So in peer-to-peer direct transactions, there is a need to buy POWR token, which is converted to the local market token SparkZ, and which will be delivered to consumers. And this is the architecture of PowerLedger. In the past, it was built on Ethereum blockchain, but now it has partnered with Solana, so I'm not sure if both Ethereum and Solana play a role, or they want to replace Ethereum in favor of Solana. Then the next layer would be PowerLedger Core, and PowerLedger Core includes elements such as oracles. We talked about oracles in the lecture on smart contracts. There is escrow management, and of course dispute resolution. Then on top of the core, there are echo chain services based on the consortium blockchain. And it also uses state channels similarly to Hyperledger Fabric. Those services include services for meter reading, token management, asset management, incentivization, and so on. And on top, the topmost layer, even though it's in the bottom in the illustration, is applications, which is called Fusebox in the PowerLedger terminology. So the applications would include peer-to-peer energy trading, autonomous asset management, charging of electric vehicles, carbon trading, and emissions, and emission tracking. And microgrid network management, and so on. So the information presented in this lecture is again based on the information provided by the Center of Excellence in Blockchain Technology, but it's also based on the PowerLedger white paper, and specific projects were based on, or illustrations about specific use cases were based on academic papers, such as the papers from Dr. Moody. And this is the end of the lecture. I would like to thank you for the attention.